Okay, so first of all, sorry, I realized that I still had some more out of 2.5 to do. So I'm going to do a couple of examples that are still relevant to 2.5, which is about continuity. So there's a problem like this on the online homework. You suppose that you have two continuous functions, f and g, or at least they're continuous at x equals 4, and then you're given the value of this limit, and then they're going to tell you either f of 4 or g of 4. And in this case, they're telling us f of 4, and then they'll ask you to find the other one. So this isn't hard if you know what to do. First of all, just to make my life easy, let me call this thing that I'm trying to find, I'll call it b. Then what is this thing that they're telling us? 18 equals this limit. If these are continuous functions, and f of x is going to 4, like f of 4 would be 4, so then the limit as x goes to 4 of f of x should also be 4. And the limit as x goes to 4 of g of x should just be b. So this, I can just say this limit is, well, f of x is going to 4, g of x is going to b. So I have this, and then I just solve it for b. So this should be easy from here. So I subtract 16, 2 equals 4 over b, and then I'm going to solve for b, but let me make a long story short here. We're going to get b equals 2. So that's it. Yeah. Then we have a problem where we have a graph and we have to state the intervals where it's continuous. Maybe I'll box this off so it looks a little bit better. So right, these pictures is all about looking at where the breaks in the continuity are. Like where, if I'm going to sweep from left to right and draw this with my pen, where do I have to lift my pen? That's roughly speaking what I'm doing here. So I could go all the way from -3 to -2 without lifting my pen, except I have a hole here. So here, this is not continuous at -3. In fact, it's not even continuous from the right. Because if I'm approaching from the right, I'm coming right up to this hole. So I would say -3 to -2 like that, because at -3 it's not continuous from the right, but at -2 it is continuous from the left. If I come up to here, I'm coming up to a point that's actually right there. So that's why I put a square bracket at -2. Then there's another interval of continuity starting here. This would be not including -2 because this is right. At -2 it is not continuous from the right. And going all the way up to -1, but then I would also not include -1. At -1, we have one of these situations going on where it's like there's a hole, and then there's this single dot kind of in the middle of nowhere, and then it picks up over here with another hole. So at -1, it's not continuous from the right or the left. So -1 is not going to be included in any of these intervals. So the next interval is going to start with -1, not including -1, and going until it looks like +1, where it looks like we have a vertical asymptote. It is not, if I'm approaching 1 from the left, it's not continuous from the left, and it can't be because this is approaching -infinity. At 1, it does seem to be continuous from the right, though, because there's this dot right here. So my next is going to start with 1, including 1, and go until, well, it looks like I have another vertical asymptote here. So 2 not including 2. And then there's one more interval. It's going to start with 2 not including 2 because this is not a dot, this is an open circle, and going until 3, and it looks like this should include 3. Okay. Yeah, so maybe the subtle point here is figuring out when to include and when not to include. But it's all about whether the function is continuous from the right or from the left. Okay. So one more from 2.5 about the intermediate value theorem. I just abbreviated IVT, but that's what intermediate value theorem means when it comes up. And so this is a theorem. I'll kind of show you through an example that it's useful to show that there's roots of equations in certain intervals. So here's how you use it. Let me skip that part. First of all, you might be given an equation. If you don't have 0 on one side, then you want to move everything over to one side so that the other side's 0. So what we're really looking for is a value of x such that x cubed minus 2x plus 1 equals 0. So I got it in that form. It's a function equaling 0, and then there's a few things for me to check. First of all, this function, x cubed minus 2x plus 1, is continuous on the interval from 0 to 2. And in order to apply the intermediate value theorem, this needs to be true. We should actually check it. I mean, it's possible that you will be given a question and you won't know whether intermediate value theorem can be used or not, and you have to really check whether you're allowed to use it. In this case, this is a polynomial. Oops. A polynomial, a polynomial is a type of elementary function. In particular, in polynomials, everything is in its domain. We know that elementary functions are continuous on their domain, so actually this function is continuous everywhere. So it's definitely continuous on the interval where it needs to be continuous. Okay, so that's one thing to check. The other thing to check is to plug in the endpoints of the interval. So the interval that we're given is 0 to 2, so I'm going to find f of 0 and f of 2. And if I do f of 0, that seems to be 1. Whoops, did I? Okay, sorry. I think I made a little mistake. I meant this to be, yeah. Yeah, I think I meant this to be a plus 1. So then this should be a minus 1. And then this should be a minus 1. Okay, sorry about that. Yeah. So then f of 0 would be negative 1. That's what I wanted to happen. F of 2 would be, let's say, 8 minus 4 minus 1 is 3, right? So what we're checking for is this one is smaller than 0, this one is bigger than 0, and let me tell you why we call it the intermediate value theorem. If I have a continuous function on an interval, and at the start of the interval, the function is negative, and at the end of the interval, the function is positive, then this function has to pass through every value in between. In other words, it has to pass through all intermediate values. I'm going to draw a little picture. This picture is not really necessary for you to draw. I'm just kind of illustrating the concept of the intermediate value theorem. But if f of 0 is -1, then it's like I have a point down here. And if f of 2 is 3, then it's like I have a point up here. And I know that this is a continuous function, meaning the graph of this function, even if I don't know exactly what it looks like, it goes from here to here continuously, meaning if I draw this graph, I can't lift up my pen. So actually, it has to pass through, like vertically, it has to pass through every level in between. In particular, we were looking for a value of x such that this would equal 0, and so that's the x-axis. So it's like, how can it get from here to here without crossing the x-axis? That's the concept of the intermediate value theorem. There's just no way to get from here to here without lifting my pen and without crossing the x-axis. So in any case, we're done. Just by the fact that we checked that this is a continuous function. We checked that at one end of the endpoint it was less than 0, and at the other end of the interval it was greater than 0. So that's all we need for the intermediate value theorem. Okay, good. Then so yeah, sorry to do this, but I'm going to go ahead and do an example out of 2.6, and I'm going to end up making another video about 2.6, but let me get through this one example before I stop this video. Say we're given a graph like this, and this has horizontal asymptotes and vertical asymptotes. And in 2.6, we start talking about things like this, the limit as x goes to infinity. So just visually, you can tell the limit as x goes to infinity by looking at values of x that go far, far to the right. Of course, we can only see so much of the graph, so I can't see anything to the right of this. But I can start to see what looks like it's going to happen. It looks like this graph, as I go farther and farther to the right, it's sort of leveling out and becoming flat, and it's approaching this line. This is the line y equals -2. So I would say that this limit is -2, just off of the graph. The limit as x goes to -infinity, I would look at values of x far, far to the left. And again, I see something similar here, that this is the line y equals 1. So I write that. Also, these aren't really new. We talked about these before, but let's talk about these again. The limit as x goes to -1. So -1 is here. This is where I see a vertical asymptote. And I see on both sides of -1. On the left, it looks to be going up and up and up. And on the right, it's also going up and up and up. So I would say this is positive infinity. Now for part D, the limit as x goes to 1. Here's 1 on the x-axis. And here I see something different. On the left, it's going down. So actually, if the limit as x goes to 1 from the left, looks like it's -infinity. But as it goes to 1 from the right, it looks like positive infinity. Those don't match. I'm getting different answers on the left and the right. So I would say this one does not exist. If they both go down, then I say it's -infinity. If they both go up, then I say it's positive infinity. But if one goes down and one goes up, I say it does not exist. If I was specifically asked to find the limit as x goes to 1 from the right, then I would say that was infinity. And if I was asked for the limit as x goes to 1 from the left, I would say that was negative infinity. But that's not what I was asked. And since those two answers don't match, then I say does not exist. Okay, so let me get ready for another video.